All right, so let's look at some of the homework problems that you've got for 2-2. Some of you guys seem to be having some problems with it, understanding it. It's really easy once you get an idea of how to grasp it. The problem is you're not used to thinking in the way that we're having to think for these limits involving infinity. So here's what I want to do. Let's actually look at this one. It says use graphs and tables to find the limit as x approaches infinity of f of x, and b, the limit as x approaches negative infinity of f of x. Identify all horizontal asymptotes. Now, I'm not going to look at the graphs. I'm just going to walk you through it. You guys can graph this, and you can look what happens as x gets larger and larger and larger and goes off to the right, or gets smaller and smaller and smaller and goes off to the left with infinity to negative infinity. I'd rather you learn how to think about these because you're not always going to have a graph to look at. So what we're going to do here is we're actually going to look at this thing, and we're going to look at the limit as x approaches infinity of 1 over x plus 2 pi, and we're taking the cosine of that. Now, what's happening with x? X is going to go in here, and then whatever this value approaches as x approaches infinity, we're going to take the cosine of it. Well, let's break this down into parts. We can look at this, the limit when x approaches infinity. Something's going to happen to the 1 over x, and nothing's going to happen to the 2 pi. 2 pi is a constant, so 2 pi is going to be 2 pi is going to be 2 pi is going to be 2 pi. So all we're focused on right here is this part right here. Now, as the bottom gets larger and larger and larger, let's say it starts with 1, and then it's going to get larger. Let's say it goes to 5, and x gets larger. It's going to go to 10, and x gets larger. It's going to go to 100, and I mean we're only to 100 when this thing's actually going off to infinity. But what do we already notice about the fractions? The fractions are getting smaller and smaller and smaller. So what's going to happen to 1 over x is it's going to go and get smaller and smaller and smaller, and it's going to approach 0. Because you're going to have 1 over 1 million, 1 over 1 billion, 1 over 1 trillion, 1 over 1 Googleplex. You're going to have huge numbers on the bottom divided into 1. If we take 1 and break it up into 1 million pieces, those are tiny, tiny pieces. So that thing's going to go to 0. So if we take this limit, and this thing right here is literally, the thing I've got circled is going to 0, we're going to end up taking the cosine of 0 plus 2 pi, which is just the cosine of 2 pi. And what's the cosine of 2 pi? Cosine of 2 pi is the same thing as cosine of 0, which is going to be 1. So the limit of f of x as x approaches infinity is going to be 1. What about when it goes to negative infinity? Well, it doesn't matter if it's going to 0, whether it's approaching it from the negative values or the positive values. Now keep in mind, it will be approaching it from the negative values, it's going to go to 0, because you're dividing 1 by some negative really large number. But the thing is, 0 doesn't have a sign, so it's still going to approach 0. So this is still going to approach the cosine of 2 pi, which is still going to be 1. All right, and then select the correct choice below, and if necessary, fill in the answer blank box to complete your choice. Now, remember, a horizontal asymptote is what value that function is going to approach as you go way off to infinity for x values or way off to negative infinity for x values. In other words, as you go way off to the right and way off to the left. Well, as we find right here, the limit on both sides as x approaches infinity and negative infinity are 1, so we are going to have a horizontal asymptote, and the y value is going to be 1. So y equals 1, remember that's a horizontal line, is your horizontal asymptote. And really, it's going to take a while to go to the next one. Awesome. All right, so with this one, you're doing the same things, but notice you're looking at a rational expression. A rational expression, remember, is anything that can be expressed as a fraction, but more specifically, the one we're talking about, the type of rational expressions we're talking about, is going to be a polynomial over a polynomial. So in this case, here's what I want you to start thinking. And this is where it gets weird because you're not normally going to think this way. Let's go ahead and say the limit as x approaches infinity of 7x to the third minus 6x plus 9 over 9x plus 8. Now, as we look at this and think about this as x goes to infinity, of course, these on top, this on top is going to go to infinity, this on bottom is going to go to infinity. Here's the problem we got to look at, though. What is going to control the value, or what's going to add the most part of the value to this top? Is the 7x to the third, the minus 6x, or the 9 going to add the most value as x gets larger and larger and larger? Well, when you get to 1 million, what's going to be larger, 7 times 1 million cubed, or 6 times 1 million, or 9? Well, of course, this 7 times 1 million cubed is going to be. So what we're going to do, and this is where it gets kind of weird because you haven't been able to do this, we're going to ignore these, because this is going to control the value of that top polynomial. It's going to be the one that's going to have the majority. When you get the x big enough, these right here are not going to be anywhere near the value of what that's going to carry. So these become negligible in this equation, or in that polynomial, that expression right there. Right? And when we think the same way down here, just on the bottom, 9 times 1 million is going to be a lot bigger of a term than just 8. 8's kind of not going to have much. Once x gets to 1, this term's already winning. So we know that this one is going to become negligible as x gets larger and larger and larger. So then essentially what we're looking at, and I'm approximating it because this is not equal to, but it's going to be approximately equal to the limit as x approaches infinity of 7x to the third over 9x. Now, when you do that, well, of course, now we can cancel out one of our x's. So we're going to get 7x squared over 9, and we're taking the limit as x approaches infinity. And what's going to happen to this? Well, the top's going to get larger and larger and larger and larger and larger. Therefore, this is going to approach infinity. So that's going to be our answer here. Now, what's going to happen when we approach negative infinity? Is anything going to change? Well, if we're using a negative number and we're putting it in here, but we're squaring it, what do we know? We're going to end up with a positive. So that's still going to go to positive infinity. Now, if this had been just 9 on the bottom, and we end up with x cubed here, then this has to be negative infinity when we approach negative infinity. But since it's a squared, the negative gets tossed out because of the squaring thing there. All right, so our answer here is going to be infinity. Good job. And here is also going to be infinity. Well done. And then our horizontal asymptotes. Well, remember, a horizontal asymptote is what value the function's approaching as you get further and further out to the left and the right with the function. Well, if it goes to infinity when you get further to the right and approaches infinity when you go further to the left, there is not a certain value that it's approaching, is there? So that means there are no horizontal asymptotes. All right, so with this one, we've got the limit as x approaches infinity of 6 minus cosine x all over x to the third. Now, you're going to do some simplification in here just so you can break this thing apart and look at it in parts. So I'm going to do limit as x approaches infinity, and I'm going to take this x cubed. Since I've got a single term on bottom, I can divide that into all the terms on top. So I end up with 6 over x cubed minus cosine x over x cubed. That is exactly the same expression, but now we're able to look at it in a little different way. Remember, when I talked to you about 2-1, we can think about these limits as two different limits. We don't have to write it out this way, but we can actually think about it as the limit as x approaches infinity of 6 over x cubed minus the limit as x approaches infinity of cosine x over x cubed. Now, this one becomes a little easier. Just looking at this one, what do we know? Well, as the bottom gets larger and larger and larger, we're going to have some number divided by a really big number, so that's going to approach 0, much like that 1 over x did before. Guys, it doesn't matter what the number is on top. If it's a constant on top and the bottom's approaching infinity, it's going to go to 0. It could have been 6 billion on top, but eventually x is going to grow to the point where this is going to get smaller and smaller and smaller. It may take it a little while, but it is. Remember, x is not just going to infinity, or x is not just going to 1,000,000 or 100 or 1,000. It's going to infinity. It's going to grow into the billions, trillions, gajillions, whatever ones you can think of. So it doesn't matter what that constant is on top. Eventually, it's going to surpass it and start approaching 0. All right, now this one over here, you got to think just a little bit different about, though. And what I want you to think about, let's take this part right here, and just as a kind of an aside, I want you to rewrite it in your head and look at it this way. Remember, this is cosine x over 1, and we just move that 1 over x cubed out in front instead of having it divided by it. So now, hopefully, you're going to recall that this is a trig function in the form a cosine x, where a was the amplitude. Now, so if this is the amplitude, remember, the amplitude tells you how far up and down this thing's going to go. If we got our center line, the amplitude is right there. That's our a. And then, of course, this down here is the negative a. So you're primarily focused on this part right here out in front. As x goes to infinity, what is 1 over x cubed going to do? Well, it's going to be just like this one right here. It's going to go to 0. So if that amplitude of this cosine value is going to 0, then the value of the cosine is going to go to 0 as well. So we end up with 0 minus 0, which is 0. Now, give me just a second, and I'll show you what that is, what that looks like as far as a graph. But let's go ahead and work this problem out, finish working this problem out first. So that's going to be 0. Before we get into this question, I want to take just a second, and I'm going to show you a graph. All right, so this is a graph of sine x divided by x. So what's happening here, and this would be very similar if it was cosine x over x. Sine x, cosine, they're going to behave similar. The starting places is just going to be a little bit different. Cosine would have been down here at 0 and gone through. Or maybe not. I don't remember. I'll have to go back and look. Anyway, all we're worried about is what's happening as x gets larger and larger and larger and larger here. And if you'll notice how far it goes above and below the x-axis is getting smaller and smaller and smaller. That's where that thing that we were talking about, the 1 over x, or the 1 over x cubed in that last problem is going to 0. The amplitude of this trig function is getting smaller and smaller and smaller, and keep in mind we're only out to 20 here. So as you get out to 100 and 1 million and all that, it's going to be even tinier. But that shows how it's going to behave as you get further out. The amplitude gets smaller, so eventually this thing is going to not go past the x-axis on either side very far at all. So I just wanted to see you guys to see that. All right, so this one right here, very, very similar to the previous one. It doesn't matter what is inside the sign. This is not like when x approached 0. Remember, in 2-1 we had a special case for sign where these had to be equal. And if they were equal, as this approaches 0, this would approach 1. Well, going to infinity, it's not. It's the same thing. You're going to think about this as 1 over 20x times the sine of 9x. Once again, there's the amplitude, and that thing's going to go to 0. So this thing's going to approach 0 as the limit of x approaches infinity. If this had been 0, then you've got to do it with the other method. Remember, it's very, very important what x is approaching. As x approaches infinity, this goes to 0. If we're doing x approaches 0, then this would end up being 20 over 9. So it's very, very different. All right, so I'm not going to do all these questions, but you can kind of get the idea. Now, right here, we're approaching 3 from the left side. So that means we're approaching 3 from 2. We're going from 2 to 3. So we're going on lower values and coming up to it. So here's the thing. Think about this. If we get 2.9 right here, and we subtract 3, do we have a positive or do we have a negative? Well, we're going to end up with a negative. And here's the thing. What happens when we have exactly 3 there? Well, we end up with 1 over 0. And if you remember, if we have 1 over 0, this is going to infinity. The reason why is this. Remember, the bottom is getting smaller and smaller and smaller because we're getting closer and closer to 0. So it's like we have 1 over 1/2, 1 over 1/4, 1 over 1/8, 1 over 1 over 100. And what do we do with these? Well, if you keep change flip, remember, you're going to keep the top, you're going to change the operation of multiplication, and you're going to flip that over. So this equals 2, this equals 4, this equals 8, and this equals 100. So the smaller the number on the bottom gets, the larger the actual value gets. So as this thing approaches 0, this thing right here approaches infinity. Now, because my bottom is negative, that means that I have a negative 0. Yes, I do realize that there is no such thing as a negative 0. You got to remember, though, this is a limit. We're not actually equaling 0. We're just getting really, 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 really close to 0. And it happens to be a negative number. So that means that this infinity is going to be a negative infinity. So we put in our negative, put in our infinity, we check our answer. Well done. All right, so like I said, I'm not going to do all these problems. A lot of these you can plug in, and if you follow the same kind of thinking that I'm giving you here, you're going to be able to figure it out. All right, let's talk about the greatest integer, though. Remember what the greatest integer is. We talked about it in 2.1. It's going to be the graph. I and t of x just simply means round it down. So from 0 all the way up to 0.99 repeating, this int is going to equal 0. From 1 to 1.99 repeating, this thing is going to equal 1. And then once it gets to 2, going up to 2.99, you get the idea. This is going to equal 2. So if we're approaching 0 here from the left side, that means that the int of 0 is always going to go down. So that means that that's going to be a -1. And as we approach 0 here, that means that this is going to get smaller and smaller and smaller. So we're going to think about this as -1 over 0, which is going to equal -infinity. Oh, wait a minute, hold on. Wait just a second here. No, we're going to have negative values down here, too. So, sorry, that's going to be a negative down here, so that's going to be a positive infinity. Sorry, about led you astray there. Remember, because we're approaching from the left side, we've got negative numbers that we're multiplying times this 4. So that's going to be a -4 times essentially 0, which is going to approach -0, which is going to give us a negative over negative, which gives us a positive. All right, these you just need to break up into parts. Do the 9, do the 4x over x minus 3, do the x squared over 1 plus x squared. Remember, with the negligible parts, you can simplify a lot of this. That 1, negligible. That 3, negligible. You can get rid of it. And then break it up and take the limit as x approaches infinity of 9, the limit as x approaches infinity of this, the limit as x approaches infinity of this, and then put them together. You're going to subtract these two and then multiply by this one. So you guys can figure that out. I'm not going to work through every one of these. All right, same thing here. Remember, you're going to divide that x into both parts and split it up. Similar here. I'm going to do the same thing. All right, vertical asymptotes. If you remember vertical asymptotes, that's where the denominator is going to equal 0 that does not cancel out with the top. So in this case, you're going to factor this denominator and you're going to get x plus 4, x minus 4. So that's what your denominator is going to look like. So now you're going to have vertical asymptotes at x equals -4 and +4. So what you're going to do to find what this thing is doing is you're going to approach, you're going to take the limit as x approaches -4 from the left, and then the limit as x approaches -4 from the right, and then you're going to do the same thing with 4, left and right, and figure out which infinity it's going to go to. Remember, with your limits, or with your vertical asymptotes, remember we would dot those in there, and what happens? It goes up and either goes this way or it goes that way. So it's either going to positive infinity or negative infinity. You just got to figure out which one. Now, remember also that if we had had an x plus 4 on top, these cancel out. That's not a vertical asymptote anymore. That's just a hole in the graph. So that's going to come in handy in the next section of 2-3. But in this case, we don't have that. So we have both of those vertical asymptotes. All right, in behavior model, you're just determining whether the thing's going to negative infinity or positive infinity as the limit, when you take the limit as x goes to infinity for the right, and the limit as x approaches negative infinity as it goes to the left. All right, now a power function in behavior model is simply what in the world is controlling this thing. What function, what part is going to define this thing the best. In this case, the 7x squared is going to be what's going to control it. Remember, as x gets larger and larger and larger and larger, the 7x squared is going to be what's going to control that thing. All right, so one like this, if you're having trouble remembering what the natural log of the absolute value of x looks like, here's the thing. Remember, natural log only, you can only take the natural log of a positive number, and the graph for it is the inverse of the exponential function. So it's like this. Now, if we do the absolute value part, though, that means that we can throw in negative numbers too, and they exist. So that's the natural log of x graph. Now, all you're doing here is you're looking at what's going to grow faster. As in behavior models, remember, our limits as x goes to infinity and negative infinity. Right is positive infinity, left is negative infinity. What's going to control the value? Is the 3x going to control the value, or is the natural log of x going to control the value? Which one's going to grow faster, really? Now, as you notice, these natural logs are getting flatter. The further out here, they're going to get flatter and flatter and flatter. The 3x is going to continue to grow at a rate of 3 times whatever the x value is. So think about that and figure out which one is going to be